Hello, everyone, and welcome to Soil Moisture 302, Hydraulic Conductivity. Which instrument is right for you? Today's presentation will be about 30 minutes, followed by 10 minutes of Q&A with our presenter, Leo Rivera, whom I'll introduce in just a moment. But before we start, a couple of housekeeping items. First, we do want this to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these to answer during the Q&A session. Second, if you want us to go back and repeat something you missed, no problem. We're recording the webinar and we'll send around the recording via email within the next 3 to 5 business days. All right, let's get started. Today we'll hear from Leo Rivera, who will discuss which situations require saturated and unsaturated hydraulic conductivity and the pros and cons of common methods. Leo operates as a research scientist and hydrology product manager here at Meter. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There, he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in Meter's hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. So without further ado, I'll hand it over to Leo to get us started.
All right, thank you, Brad. Today we get to discuss one of my favorite topics, which is measuring hydraulic conductivity in soils. It's something I've spent a fairly large portion of my career working on. So just a little bit about myself. My background is in soil physics and pedology, and a big portion of that was spent measuring soil hydraulic properties throughout the state of Texas. Over my career, I've gained about 12 years of experience measuring and interpreting soil hydraulic properties and looking at soil moisture release curves. And that's really helped me gain a really strong understanding of different techniques for measuring soil hydraulic properties, what the pros and cons are, and where they fit and where they don't fit. So I'd actually like to start off today's virtual seminar with a question. So the question is, I need to measure hydraulic conductivity for my research. What type of measurement approach should I use? And this is a common one that we get, or a common situation we deal with when trying to figure out what is the right instrument or the right approach to measure soil hydraulic properties. And so first, to start off, I think it's good to go back to the basics and think about what is hydraulic conductivity. So as we all know, hydraulic conductivity is a measure of the ability of a porous medium to transmit water. And this can be in saturated or unsaturated conditions, and that value will vary depending on which condition you're in. But I think what's really important is to take into account what factors actually affect or what determines hydraulic conductivity. And there are many components that affect or change the hydraulic conductivity of soils. Obviously, it starts with basics. What is the soil texture? What's your sand, silt, clay content? And what's the makeup of the soil and how is that changing across different sites? But it's a lot more than just soil texture. Soil structure plays a huge role in hydraulic conductivity. What is the structure type? How strong is the structure? How stable is it? Other pieces that also play a big role are biopores. Are there worm channels, decaying root channels? All of these things are going to have a huge impact on the soil's ability to transmit water. Other components obviously are compaction or the differences in bulk density. That's obviously going to have a huge effect because the more compacted, the lower the hydraulic conductivity is going to be. And another piece that can play a role is the water content or the water potential. So the initial water content or water potential of the soil. Studies have shown that depending on what the antecedent soil moisture is, you can see changes in soil hydraulic conductivity. And I think that has a lot to do with shrink swell soils especially, but it can also play a factor in non-shrink swell soils. So it's all of these things are pieces that you need to take into account when thinking about measuring hydraulic conductivity. And so just to visualize this, we have a graph here showing the hydraulic conductivity changes of 3 different soil types: a well-structured clay soil, a structureless sandy soil, and a poorly structured clay soil. And on the y-axis here, we're looking at the hydraulic conductivity, And on the x-axis here, we're looking at the change in the status or the water potential of the soil. So right at this intersect here, this would be at saturation. And as we go to the left, it's going to become less saturated. And what we see is obviously as the conditions change, the conductivity of the soils change for all three types. And what's really important to take note here, obviously, is the difference between the well-structured clayey soil and the poorly structured clayey soil. So as we approach saturation, structure is going to begin to play a much larger role in the soil's ability to transmit water. And in some cases, for example, the well-structured clay soil can have a higher hydraulic conductivity than the sandy soil. So again, it's not just texture alone that is controlling the soil's ability to transmit water. And so as we dig deeper and start thinking more about what we want to measure, we then have to start thinking about saturated versus unsaturated hydraulic conductivity. So when we're thinking about saturated hydraulic conductivity, the main factors that really play a role in saturated hydraulic conductivity, or what makes up saturated hydraulic conductivity. So when we're measuring KSAT, all of the pores in the soil that are able to contribute to the fluxes are. So there's not really anything limiting which pores can contribute to transmitting water, minus them potentially being closed off. This saturated hydraulic conductivity is primarily driven by gravitational forces. So it's just something to keep in mind. But another piece that's kind of important to keep in mind is in most sites and most conditions, this is a less common state of flow in soil. So if you're trying to understand water movement throughout a season, you're going to need to know more than just saturated hydraulic conductivity. Now let's jump over to unsaturated hydraulic conductivity. Unsaturated hydraulic conductivity is going to vary depending on the pore sizes, which are able to contribute to the water fluxes. And what's controlling this is actually the water content or the water potential at the given time of the soil. And where the water is coming from. If it's moving from one side of the soil to the other, what's your gradient there in terms of water potential or water content? Those are all things that are going to play a role there. So when we think about unsaturated hydraulic conductivity, you'll typically see it referenced to a given water potential or a given water content, because as that state changes, there are less pores that are able, or more pores that are able to contribute to the fluxes. So that value is going to change. And so it is a moving scale. Unsaturated hydraulic conductivity is primarily driven by matrix forces. So it's really common to think about unsaturated hydraulic conductivity when we're thinking about water migration throughout the vadose zone. And as you can imagine, this is a more common state of flow in the soil. Typically in most sites, we're primarily in unsaturated conditions. And so water migration is going to be occurring more commonly in this state. So let's think about applications and where you'd want to measure saturated versus unsaturated hydraulic conductivity. So as we showed before, soil structure and macropore effects are going to be more prevalent in the saturated conditions. We're going to be able to capture those. So let's say, for example, I'm trying to look at maybe a soil health impact or improvements in soil structure or those types of things. We're not going to really see something like that when we're measuring unsaturated hydraulic conductivity. So saturated hydraulic conductivity can be a lot more powerful when trying to look at these types of effects. It's also obviously in groundwater flow, you're going to be dealing with primarily saturated conditions there. So that's going to be more of an important measurement to make. And also when we're looking at green infrastructure assessment, so looking at a city's ability to, or areas in cities where we're trying to infiltrate more water and those types of things, we need to know what our max capabilities are. And that's where saturated hydraulic conductivity is going to be more critical when looking at low impact development types of things. With unsaturated hydraulic conductivity, it's really powerful when trying to understand unsaturated water movement in the vadose zone. And this is especially important when we're actually trying to model fluxes. So if we're trying to model water migration through the vadose zone, we need to know the unsaturated hydraulic conductivity curve. And so that plays a really important role in modeling. And the tools for measuring unsaturated hydraulic conductivity can also be really powerful when actually trying to look at repellency or hydrophobicity. There are techniques available for the field methods to actually estimate the hydrophobicity or the repellency of the soil. So let's go ahead now, and now that we've covered that, let's jump into the methods for measuring hydraulic conductivity. First, we'll start with saturated hydraulic conductivity. And typically when we think about these measurements, we break them down into either laboratory methods or field methods for measuring hydraulic conductivity. In the lab, we have flow cells and the KSAT device, which are all based kind of on the same principles, and we'll discuss that here shortly. And in the field methods, we have ring infiltrometers, borehole permeameters, and pressure infiltrometers. In this presentation, we're going to focus primarily on the ring and borehole permeameters, just because pressure infiltrometers are less commonly used. So when we're thinking about laboratory methods, all laboratory approaches for measuring, or almost all laboratory approaches for measuring saturated hydraulic conductivity, involve collecting a core sample from the field or repacking a core from the field. Now, ideally, if you want to represent the true field conditions or have a closest ability to represent water movement in the soil, you're going to take intact cores, because repacking a soil in the lab, you don't have any of the structural components or the macropores that would actually be present in the field. So if you can take intact cores, I strongly recommend doing that if you're going to use a laboratory approach. And with both approaches, so when we think about the flow cells and the KSAT device, both approaches involve taking those core samples and measuring a steady state flow rate as water passes through the saturated sample. We want the sample to be fully saturated before we start taking that steady state flow rate measurement, but they're all based on the same principles. So with the flow cells, we have a core sample where we're passing water through and we're measuring that flow rate. And the KSAT device is the same concept. We have a core sample, we have water that is flowing through, and we're measuring that flow rate of the water through the core sample. So both of these approaches are very similar. And both approaches, we can use a constant head or a falling head technique. And really what differs there primarily is the analysis at the end, how we get to that final KSAT value. Now, an automated device can really simplify these measurements. To automate a flow cell, it usually takes a little bit more work and sometimes take a little more dedicated lab space. With the KSAT device, you have the automation already built into it, and they're a little more mobile, so you don't have to have dedicated lab space for a device like this. So let's just think about the pros and cons for the laboratory methods for measuring hydraulic conductivity. So some of the main advantages of the laboratory approach is the calculations are relatively simple. And one of the main things that makes these simple is we don't have to do a correction for three-dimensional flow, which is something you'll have to do with field methods, which we'll discuss shortly. And what's really cool about lab methods is it allows us to separate different horizons or separate the different components of the soil and measure each component's ability. Whereas in the field, we're just measuring the sum of the whole, essentially. And this is really advantageous because we can also store multiple samples. So depending on your time constraints, this can be really a pretty strong reason to think about a laboratory approach. And for the most part, depending on your setup, your apparatuses, it's a fairly easy setup. One of the disadvantages with laboratory methods is, especially when working with expansive soils, if you take a core sample of a soil that has high shrink soil capacity when it's in its drier state, when you go to saturate that sample, it's going to swell and it's going to compress in that ring as it swells, or even swell out of the ring. And so you're going to see some issues with that. And so you have to be careful with your timing if you're sampling expansive soils. There are approaches that are not a confined ring, but often those require a much more expensive setup. And another disadvantage of laboratory methods is the values typically differ from field methods. It's very rare that you get these field methods to match up with laboratory methods. And one of the main issues with that is with a core sample, you may have open-ended pores that are not open-ended in the field. You're also only looking at individual layers, so you're not seeing how things work together as a part of the system. So there are a lot of things that can result in differences between lab and field methods. Depending on your apparatus, it may require additional equipment to automate, primarily with the flow cell approach. And typically with flow cells, you're going to have dedicated lab space that you need for that. And one other disadvantage of the laboratory method is the small surface area. So you're taking a small core ring, maybe it's a 5 centimeter up to maybe 8 centimeter core. So you're looking at a pretty small area. So when you're thinking about representative elementary volume and spatial variability, you're not encompassing as much. So that's a bit of a disadvantage to this approach. So let's think about field methods now. One of the most common methods for measuring infiltration in the field or hydraulic conductivity in the field are ring infiltrometers. And ring infiltrometers essentially involve taking a thin-walled, open-ended cylinder and driving that cylinder into the ground. And then we're going to infiltrate water into the ground and through this cylinder using typically a constant head or a falling head approach. And with these, you can have various cylinder arrangements from a single ring all the way up to a triple ring which is not nearly as common. So as we dive a little more deeper into ring infiltrometers, the most common approach for ring infiltrometers is the double ring configuration. This is what most people use. It's what's written into a lot of the standards. So it's a fairly common approach. We also have the single ring infiltrometer. And when you're thinking about both approaches, when you're infiltrating water through this ring into the soil, you can imagine, so as the water is entering the soil, it's not only going down vertically, it's also going to begin to go laterally just due to some of the matrix forces and the sorptivity of the soil actually pulling that water in the lateral direction as well. And so when we're making these measurements, because hydraulic conductivity is that one-dimensional KSAT value, we need to do a correction for three-dimensional flow to get an accurate hydraulic conductivity. With a double ring infiltrometer, we have a measuring cylinder, and then we use a buffer cylinder to try and buffer that inner ring from the lateral fluxes. But that outer ring still does not completely buffer that inner ring from lateral fluxes, and that will vary depending on what the soil type is, how much actual buffering you're getting. So with both approaches, we have to make corrections for three-dimensional flow, and those corrections involve making an estimate of what the soil properties are, or trying to estimate what the alpha value is, this macroscopic capillary length factor that we use to estimate the sorptivity, and then go in and do our corrections for three-dimensional flow. Now, we run the risk of making errors there because we're typically making assumptions about what the soil type is and what the structure is. And so we can sometimes use a wrong value to correct for three-dimensional flow. So there is another approach to help overcome this issue and actually simplify the analysis, or simplify the analysis when trying to do the corrections for three-dimensional flow. And that's the dual head method, or the multiple ponded head analysis approach. With this multiple ponded head analysis approach, we infiltrate water at two different pressure heads, and that allows us to actually measure what this alpha value should be and do a direct correction for three-dimensional flow for each individual site. So we're not dealing with having to guess what the soil type is, which it really simplifies the workflow and makes things a lot easier, and also reduces the potential for error in the measurement. It's still a ring infiltrometer approach, so it's very similar to the single ring infiltrometer, but instead of having to make an estimate of the values for three-dimensional flow, or taking a guess at it, we're able to more directly measure what that should be. And the way, for example, the Saturo works is we infiltrate water at a constant head, and then we use air pressure to impose those higher pressure heads. And when we look at a typical infiltration curve from a device like this, using this multiple ponded head analysis approach, this is what that curve is going to look like. So we have a higher initial infiltration, and as the soil begins to saturate, we should see a decrease or a steadying of that infiltration rate as we approach our steady state values here. And when we increase the pressure head, which you can see an increase in the pressure head as we see this increase in the hydraulic conductivity, or in the flux, we see that. And so you see an increase in the flux, and then we decrease our pressure head and it comes back down. And in doing so, we're able to use that increased flux to actually go in and estimate the sorptivity and do a correction for three-dimensional flow. And so the analysis for this looks like this, where we're taking the average infiltration rate, or the average flux at the two different pressure heads, and then using that to directly do our correction for three-dimensional flow. So we're using the the flux at the two different pressure heads along with the actual pressure to do corrections. And it's a much more simplified approach, and it helps it make it easier to do the final calculation of hydraulic conductivity. So another common approach in the field used for measuring hydraulic conductivity is the borehole permeameter. And what the borehole permeameter, what this involves is augering a hole to your desired depth and using a device like this to maintain a constant head of water inside of that borehole. And then we're measuring that infiltration as the water is entering in that borehole and going into the soil. There are several designs for these types of borehole permeameters. They have a really big advantage that it allows us to get down deeper and actually look at individual layers. This is really not a good approach if you're trying to do measurements from the surface, but if you want to get down deeper and measure the different soil layers, this can be a really advantageous method. Similar with the ring infiltrometers, you do have the ability to do the single or multiple ponded head analysis approach. With that multiple ponded head analysis approach, again, it allows you to do a better determination of that alpha value and help simplify the three-dimensional flow, or the three-dimensional flow corrections. One potential issue with a borehole permeameter is when you're augering a hole, you do run the risk of smearing soil pores. So you could potentially alter the soil properties, which would then affect what your actual hydraulic conductivity is. So it is something you have to take into consideration with this approach. And because it's in an augered hole, typically you have a smaller area than what you would get with like a ring infiltrometer. So again, we're dealing with spatial variability and trying to get that representative elementary volume. So to summarize the field methods, let's think about the advantages and disadvantages of each. When we're thinking about ring infiltrometers, because we're able to use larger rings, we're able to encompass more spatial variability, which helps reduce the number of measurements we would have to do on a site to kind of cover what that spatial variability is and get a more accurate assessment of the overall field's ability to infiltrate water or the field's hydraulic conductivity. With ring infiltrometers and with the results oftentimes better represent field conditions because they're infiltrating directly from the surface. We're dealing with all of the correct interactions of the soil layers and the pores and the structure. So that's a pretty major advantage to field approaches. Now, one of the disadvantages to a ring infiltrometer is it is time consuming. These measurements typically take anywhere from 1.5 hours to 2 hours, if not longer, depending on the soil type. And depending on the type of device or type of approach you use, you do have to do that estimation of the soil properties to get that alpha value to correct for three-dimensional flow. Now, if you use something like the dual head approach, then that does help simplify this and helps overcome this disadvantage. But again, these are things that you have to consider. And with double ring infiltrometers, what we found is that buffer, or what research has found and what's shown in the literature, is the buffer cylinder is often not effective at buffering that inner ring from lateral flow. With the borehole infiltrometers, the measurement, with the ability to do the multiple head analysis, we can improve the analysis or get a better estimate of the alpha value. And what's really nice is it allows us to get down to deeper layers and understand deeper layers. So if you're trying to do this in the field and you want to understand different layers and how they're contributing, this is a really strong reason to go with a borehole approach. Some of the disadvantages with the borehole infiltrometer is they're typically a more complex apparatus to set up and to get going. It does require a little augering and those types of things. So you do have to be careful with that. If you're using the multiple head technique, it is going to, again, require more time to actually take the measurement. With all field methods, really, you're going to be dealing with a fairly long measurement time. And so often at times it's nice to actually set up multiple systems if you can to get more measurements within or at the same amount of time. And so it's just something to consider when you're thinking about field methods. And many of these devices are not automated, so it does require a little more work in the field to keep up with them and to actually make the measurements. So now let's jump over to unsaturated hydraulic conductivity. And again, we're dealing with the we're dealing with typically either a laboratory approach or a field approach. With a laboratory approach, we have typically either Tempe cells or flow cells. So it's going to be very similar to what you saw for the saturated hydraulic conductivity. And then we have the evaporation method, which is another approach that is beginning to be used more commonly for making those measurements. And then we also have in the field, the primary device that's used for field measurements are tension infiltrometers. That's really the only one that I'm aware of that's used for doing unsaturated hydraulic conductivity in the field. So with flow cells or Tempe cells, it's a very similar setup to what we saw for the flow cells for measuring saturated hydraulic conductivity. But one of the main differences is that we actually have to embed 2 tensiometers into the core to actually measure the water potential directly in the soil core as we're infiltrating water through the sample. And another piece that is different with this approach, so one, we're having to make a measurement of suction or water potential, but we're also going to have to control the flow rate of water into that core sample. So instead of just imposing a constant head of water, we actually have to have a controlled flow rate into the sample. So it does make this setup a little more complicated. But what's really nice with this approach is we can start with a low flow rate. And what we're doing is measuring we're going to measure the suction or water potential at the 2 tensiometers with that given flow rate. And once those 2 tensiometers equilibrate or read the same water potential, and based on what that flow rate is, we know that that's a given hydraulic conductivity for that given water potential or water content. And so we can then step the flow rate up and get another point on the unsaturated hydraulic conductivity curve. So it's really advantageous when using this approach, is you do have to step it up. Now, as you can imagine, this is going to be relatively time consuming and take a little bit more of your time to actually do the measurements. Another approach in the lab is actually the evaporation method. And the evaporation method was first introduced by Wind in 1968. And what this involves is taking a saturated soil core and allowing it to evaporate at a relatively constant evaporation rate in the lab. And while we're evaporating this soil core, while the water, and I should also state that the evaporation only comes from the surface of the soil core. So we're getting a gradient throughout the core. While the evaporation is occurring, we're taking simultaneous measurements of matrix potential and water content throughout the core. And with this original setup they have here, you can see they actually have 4 tensiometers embedded in the core measuring the change in water potential as the core is drying. So as you can imagine, that's quite a bit of setup to get all of these tensiometers embedded in the soil core. That approach was later simplified, and so it's known as the Wind-Schindler simplified evaporation method. And the way it was simplified is it was simplified down to 2 tensiometers at different heights within the soil core. And so that simplified the setup of the approach. And so with the HYPROP, that's what we're using. The HYPROP uses the simplified evaporation method. And so we have that same saturated soil core. We're measuring the change in water potential and water content simultaneously as the soil sample is drying. And with that, as the sample is drying, we begin to get a gradient in the water potential at the top and the bottom tensiometer. And using the inversion of the Darcy equation and that difference in water potential changes and the change in water content allows us to actually go in and directly estimate or measure what the unsaturated hydraulic conductivity is along the curve. So the nice thing about this approach is once you set it up, it's completely automated, and so it doesn't involve a lot of your interaction to get each individual point. It just measures each individual point as the soil is drying, so you get a lot of detail in that curve, which is really nice. So when thinking about laboratory methods, the main pros and cons for each of these approaches. So with flow cells, what's really nice, and this is actually an advantage for both approaches, the flow cells and the evaporation method, is we get simultaneous water transmission, so hydraulic conductivity measurements, and we get retention properties for the soil sample. So we're getting that soil water characteristic curve. With the flow cells, you actually can do both the saturated and unsaturated flow parameters, which is a really nice advantage to this approach. Some of the disadvantages with the flow cells is it does require a method of maintaining a constant flow, so your setup's going to be a little bit more complex, and there's a lot of operating and controlling that setup. With the evaporation method, again, you're getting those water transmission and retention properties. What's really nice is once you get it set up is the approach is completely automated, or the measurement is automated from there on out. And so you just wait till the measurement is done or the soil is done evaporating, or once both tensiometers cavitate, and you then post-process that data and you have your unsaturated hydraulic conductivity curve. And because it's automated like this, we have excellent measurement resolution. So we get a lot of detail on the unsaturated hydraulic conductivity curve. One of the disadvantages of this approach is near saturation, we're not going to be able to get good enough resolution on the changes in water potential to get an estimate of unsaturated hydraulic conductivity near saturation. So, so you may have a little bit of a gap between your saturated hydraulic conductivity and your unsaturated hydraulic conductivity that is picked up with the evaporation method. There's a little bit of a learning curve with learning how to use and degas a tensiometer, but once you get that down, it's relatively simple. Another disadvantage is you're only measuring on the drying curve. And so because of that means we're only getting desorption characteristics. So we're not really going to understand hysteresis or anything. So that is just something that you have to take into account if you want to have both wetting and drying properties. So in the field, the primary tool that's used for measuring infiltration is a tension infiltrometer. And that involves a device that has a porous plate, and you would place that porous plate on the soil. And what we're doing is imposing infiltration, or we're allowing the water to infiltrate under an imposed suction. So with something, so we have a mini disc infiltrometer here. With something like this, we have a bubble tower or a Marriott bubbler that's allowing us to control what that suction is. So the deeper we insert the rod into the bubble tower, the higher the imposed suction is. And so we're actually limiting which pores can contribute to the flux with a device like this. And as you can imagine, like with all the field methods, we have to do corrections for three-dimensional flow. There's nothing that's going to limit the water from moving laterally. So because of that, we have to estimate what these soil properties are again. We have to make corrections for three-dimensional flow based on those soil properties. So again, we have some post-processing that could potentially have some error. And so it is something to keep in mind when you're thinking about this approach. What's really nice about tension infiltrometers as well is, again, we can use them to actually, there are approaches available to determine repellency as well. And so we can make, when we're doing, if you're doing post-fire work and you're trying to understand how hydrophobic the soil is after a forest fire, or if you're just interested in hydrophobicity in general, these can be really useful tools for trying to make that estimate. So with pros and cons to the tension infiltrometer, we can control the suction with a tension infiltrometer, which is really nice when we're trying to get individual points of unsaturated hydraulic conductivity. Larger discs allow us to account for more spatial variability, which is an advantage over the laboratory approach. And we can use these to do an estimation of the sorptivity or and repellency, or that the hydrophobicity of the soil. One of the disadvantages to tension infiltrometers is if you're using a steady state method, they are time consuming. And so again, with most of these field approaches, your measurements typically are going to take a good amount of time in the field. And again, we have to make an estimation of soil properties to correct for three-dimensional flow. So let's just summarize everything that we've discussed about all these different approaches. And the way I like to break it down is really between lab instrumentation and field instrumentation. So with lab instrumentation, one of the main strengths is we have controlled conditions. So we know exactly what's happening. We know we're controlling the water that's moving into the soil, and we know where it's going. And so it simplifies things because we typically don't have to do any corrections for three-dimensional flow. So typically it's a more accurate measurement than what you would get in the field. And it's really advantageous if you're time constrained in the field, because you can collect a lot of core samples and bring them back to the lab and run them as you have time. And so you're not dealing with having to take a lot of measurements in the field. Limitations to laboratory approaches is, again, this doesn't really take into account field conditions. And depending on the apparatus that you're using, it could be a fairly complicated setup. So something to consider when looking at lab approaches. With the field instrumentation, we do a better job of understanding the variability and the real-time field conditions. So we just get a better representation of what actually happens in the field. And depending on the approach you use, usually the installation and setup is relatively simple. And there are devices available to automate these measurements in the field and make it a lot easier. Especially what's nice about the field approach, if you use an automated device, you can set them up and go on and do other field work that you might need to do while the measurement is occurring. Some of the limitations, and this is really a limitation with all approaches, is spatial variability typically requires more measurements. So if you're trying to do a good job of encompassing and understanding the spatial variability in the field, then you're going to have to go out and make more measurements. But if you can automate this, that does improve your ability to go out and make more measurements at the same amount of time. And typically you have more data to analyze. There's a little bit more post-processing involved. We're dealing again with uncontrolled conditions. We don't know exactly where the water is going. We don't know how the water movement is moving through the soil. And also we're dealing with the weather. So if it's snowing or if it's frozen, then we really can't go out and make measurements during these times of year. So you typically have a more limited window, depending on where you're at, as to when you can make measurements. And with any approach, really a poor installation or poor approach or a poor setup can result in inaccurate measurements. So it's important that you think about using a more simplified, if you're using easier to set up tools, there's less chance you're going to have error due to your setup. So we'll finish this off with some common questions and things that I like to consider when thinking about these different measurements. I think the first thing you think about is, how long do I actually have to take measurements in the field? If I'm time constrained in the field, then you're probably going to have to think about taking core samples and bringing them back to the lab and measuring them as you have time. But if you're not, then I typically tend to push people towards field methods because they better represent field conditions. And again, are you more interested in field scale effects or individual parts of the soil? If you want to get field scale effects, you're typically better off with field measurements. But if you actually want to understand each individual layer or component of the soil, then a laboratory approach actually can be more advantageous because you can actually separate those components out. And one common question I get is, how many measurements do I need to take? If you look through the literature, I typically recommend 3 measurements per measurement location. Just getting measurements in triplicate helps you better encompass some of that spatial variability, and then per site, that's going to vary depending on what your variability looks like in the site. So it's good to try and make an assessment of how variable your field is to make an assessment on how many measurements you need to take in a site. So with that, I'll open it up to questions.
Awesome. Thank you, Leo. So yeah, we'd like to use the next several minutes to take some questions from the audience. Thanks to everyone who has submitted some questions already, and there's still plenty of time to submit your questions. Just type it into the questions pane, and we'll try to get to as many as we can before we finish here. There are some, if you do have specific questions or questions that are specific to our instrumentation or others, or if there are any questions that you do submit and we do not have time to get to them, we do have them recorded. And Leo or somebody else from our environment team will be able to get back to you via email in the next day or so. So feel free to submit any and all questions, and we'll try to get to as many as we can here. So let's look at this first one here, Leo. I'm gonna go out on a limb here and say that plant material will affect hydraulic conductivity in your soil cores. How will it affect it?
Yeah, that's a really good question. And yeah, and actually, it's interesting in talking with some people about some of the work that they've done and looking at different land uses and those types of things. Even in the field, you obviously would expect to see an impact from the root distribution and the amount of roots that are present in the soil, because they do impact the soil's ability to transmit water. But it will ultimately impact the measurement So if there are root channels or roots in the soil, it may decrease the soil's ability to infiltrate the water. But again, this is what's present in the field. I mean, if we're trying to represent field conditions and actually represent what's happening, or how the water is going to infiltrate in the field under a given condition, it's important to take that into account. So the roots, especially if you have a high root density, you may see a decrease in the hydraulic conductivity, but that is what the field conditions are. Now, as that season goes on, you may see more decayed root channels and those types of things, which will ultimately improve the soil structure and have more biopores, which at some point in time will increase the hydraulic conductivity. So they do have an impact, but they're important to take into account.
Okay. Using the double ring infiltrometer, what will be the measured saturated hydraulic conductivity?
That's a really good question. So with the double ring infiltrometer or with any ring infiltrometer, what we're doing is we're infiltrating water until we reach a steady state. And then with the once we have a steady state flux or a steady state infiltration rate, we take that value for the steady state flux, and then we apply corrections to that based on the ring insertion depth, the height of the ponded head of water, and then corrections for the three-dimensional flow, also the ring, the radius of the ring. So there are a bunch of factors that go into correcting that value, and then they ultimately give you the saturated hydraulic conductivity. The piece to be careful with these corrections is that the component for correcting for three-dimensional flow is based on some intrinsic soil properties. And if you don't have a measurement of them, you have to essentially guess at what those properties are. And that if you take a wrong guess, or if you pick the wrong value for alpha, you could wind up with an inaccurate hydraulic conductivity. So just something to be careful with.
All right. This one just came in. Which method, this is an irrigation management question, Leo, for you. Which method would you suggest as best when designing a drip irrigation system and selecting an appropriate dripper flow rate?
Oh, that is a really good question. You know, when I think about drip systems, and I'm not a complete expert on irrigation systems, but when I think about drip systems, you're dealing a lot with I mean, you're somewhat saturating the soil, but you're also dealing a lot with unsaturated movement of water, because with drip systems, you're going to get a lot of lateral movement of that wetting front as it's coming in. And ideally, I think that's what you want. So it might be important to understand, unsaturated hydraulic conductivity closer to saturation, just to get an idea of how fast that water is going to be moving through the soil, because it's going to be slower than what it would be under saturated hydraulic conductivity. But it also helps you kind of understand how it's going to migrate through the soil and what that wetting front might look like as well.
Okay. See, I think we might have time for one or two more here. We do have several questions coming in about the HYPROP. Leo is an expert at the HYPROP, and so a lot of those questions he will have to get back to you via email, but we do have them recorded, and that way he can get into much more detail. You can have a good conversation back and forth with that. How about with, here's one here. When working with smart lysimeters with tensiometers, using a field method for measuring KSAT would interrupt the other experiments. Is there any way to use the measured water input of precipitation and the tensiometers to build a curve over a longer time period?
Oh, that's a good one. Yeah, I think to a point that's possible. And when you think about, like, for example, what we're doing with the HYPROP is we're taking two measurements of water potential and measuring that gradient, or even with the flow cells, we're using that water potential measurement again. And we have essentially a known water content and known changes in water potential. I think it's possible to do it with the lysimeters, but you would need to really have a good understanding of the actual water flux of water coming in. And then knowing where that water is moving through the column. I anticipate it is possible, but you're going to have to have good estimates of your water coming in and reliable water potential measurements, which I think you can do with the tensiometers. So, but yeah, it's not going to be a super easy approach.
Okay. All right, last question. How would you make saturated hydraulic conductivity measurements in soils that have cracks?
Yes. So this is something I spent a lot of time doing because a lot of my research was in vertisols, which are highly expansive soils in Texas. And we oftentimes had to deal with cracking soils. Almost so much to the point where we actually made a measurement on a site that we didn't know there was a crack, and we actually went through an entire 500-gallon water tank on that one measurement. So cracks can really impact your measurements, but they're really hard to measure because they can have the ability to transmit so much water. So my recommendation is to try and make your measurements when the soil isn't cracked. That way you have a better measurement of the intrinsic soil properties themselves. And then if you know the soils are cracking, we can use modeling to estimate the amount of water that would flow through the crack depending on the size, because that's a relatively easy thing to estimate if we can estimate the crack sizes. But it's really hard to deal with expansive soils. Expansive soils make a lot of measurements tricky. So my recommendation is time your measurements when they're not cracked, which is what we tried to do. But if they're smaller cracks, then you can measure directly over them, but you're going to see a probably fairly high infiltration rate.
All right.
So
thank you, Leo. That's going to wrap it up for us today. Again, thank you for joining us. We hope you enjoyed this discussion as much as we did. And again, thank you for all of your great questions. Again, Leo will be able to get back to those whose questions were not answered yet. Also, if you do want to know any more information on this topic or on the instrumentation involved in your research, please visit us at metergroup.com. And as well as please consider answering the short survey that will appear after this webinar is finished to tell us what types of webinars you'd like to see in the future. Look for a recording of today's webinar and presentation in your email. And again, stay tuned for future Meter webinars and have a great day.